Before I said way back at the beginning, we're going to just say we're going to take time step 1 and time step 2 and not worry about what happens in between time steps, but sometimes we do need to think about that. So let's say we're modeling something year to year, but we want to change it to month. We like to keep the delta equation the same, like delta is some constant times the previous amount. But maybe we can change our update formula to say, now that we're doing month to month, we don't want to use the delta for a whole year, just for 1/12 of a year. So let's go try that in compound interest sheet. This is a copy of the compound interest sheet. So I'm going to leave this 1% interest per year as it is, and this delta formula is still 1% of my account balance at the start of the year. But now I don't want to say this is time step number, this is time expressed in years. But if I want 1 month to go by since time 0, I would add 1/12, for example. So I could do that, and then I could say, if I'm earning interest at 1% per year, how much do I earn after a month? Not a whole $10, but that $10 times however much fraction of a year just happened. So I could say current time minus the previous time. You can call that delta t. And then so it's only $1 now, less than $1 probably, because it's dividing by 12, so I'll show the full precision there, not that we really need it. And then fill that down, and now instead of doing 600 years, I'm doing only 40 because I'm taking 12 times as many steps, roughly. And we can see it's just increasing $10.01 per year for 1/12 of a year. It's really nice to do this rather than having like a delta t specified up here, because the time change doesn't always have to be the same. If I wanted to, I could put a number here that maybe I wanted to step 1.5 months, just that once, and this formula will account for that. This formula will account for that, and then after that it'll just use whatever time values are there. So I really encourage you, if you've got a column of time here, compute the delta t for each row as you go, rather than just saying I have one global delta time up at the top. So now I'll give you a chance to practice it. With our Tylenol sheet, we had this decay rate per hour, but what if I wanted to do it every, not 1 hour, but 1/10 of an hour? So I could add 1/10 each time there. And then how would I have to change this formula? I don't want to change this delta formula because that's telling me the change rate per hour. I just want to account for the fact that I'm not going a whole hour into the future from the previous time point. So if you keep making delta t smaller and smaller and do some by hand symbolic work, what you get is a differential equation, which is also itself a lot of fun. And do you end up getting exactly the same results? Let's go take a look. So here for compound interest, let me go back to 1/12 of a year at a time. After 1 year, I'd have $1,000, 10, another 10, and 4 pennies. Compare that to after a year with our initial model, I would have $1,000 plus the $10 and not the 4 pennies. So it's pretty close, but not exactly the same. In some models where stuff is changing really quickly, you do have to make sure you take really small time steps to even get reasonable answers there.